and let me know when it's started.
I just clicked
Should be started now.
Okay. All right. Thank you very much. All right. Good afternoon, everybody. Let's get started. We're really glad that you guys are all here today for our Community of Practice Quarterly Telecon. We have a great lineup of presentations today. I'll give some really quick mission and applications updates, and then we will hear from Kirk Knobelspiesse and Meng Gao on our on new polarimetry products that are rolling out. First of all, a little bit of logistics. I'm asking questions today. You may notice we're in Teams. We were in WebEx, but it's still the same setup. Everybody's mics are muted. Please type your questions in the chat, and then we will answer at the end of each talk as time allows. And from there, let's dive right into the main mission update, which is our version 3.1 processing. So you guys would have received an email about this as well to the PACE community. And so basically, the PACE science data segment has started the version 3.1 processing for all OCI products, including completing a full mission reprocessing of level 1B products to incorporate a minor correction. Also initiated the version 3.1 near real-time processing of all of the OCI level 1 and 2 products, level 2 and 3 products from the 2nd of July forward, and then stopped the version 3 forward stream processing. So all forward stream is now v3.1 for these products, and a full mission v3.1 reprocessing of all of the OCI level 2 and level 3 products is expected in the coming weeks. And you can now get the ones that are ready, you can now get the available products, the version 3.1 ones from NASA's Earth Data Search. We also are having more products are coming with this update, and they will be appearing in Earth Data Search as they are available. For example, we have OCI aerosol products over land, ocean, and clouds from the UAA algorithm. There's also going to be SPEXone aerosol products over land and ocean from the RemoTap algorithm. SPEXone aerosol and ocean color products from the MAPOL algorithm. HARP2 cloud products from the GIS polarimetric cloud algorithm, and HARP2 aerosol and ocean color products from the MAPOL algorithm. So that's a lot of details, and the big takeaway is that we have a lot of atmospheric products coming out, rolling out with this processing, and we are going to hear about some of them in our talk today from Meng. And there's also the important note that the calibrations for all 3 of the sensors on PACE are still at version 3. So that means all the level 2 and 3 product collections derived from these V3 calibrations are tagged as version 3.x to show that difference, to kind of indicate that provenance. Beyond these updates, there's an array of new products, other ones that are coming up. They're at various stages of integration and testing, but they're close on our horizon. Products like our trace gases, nitrogen dioxide, and ozone, and a few others are also ahead. We will let you all know as those evolve. As for one more update for PACE applications, we have a lot of event updates. On October 2nd, we have an early adopter hack day happening. This is an event that we're hosting, kind of a mini hack day, half day for our early adopters. And then we have another community of practice telecon like this one, also on polarimetry, but it'll be part 2 of 2. You will have some more great speakers on polarimetry products rolling out from PACE. And then October 23rd, we have the PACE Land Data Users Group quarterly meeting for those of you that are interested in working with the land data. For all of these events, check out that website address, our events page on our website, to get all the details, to get the registration, the agenda, etc. Also, there's a GeoHealth Community of Practice Air Quality Working Group meeting that we're going to be presenting some PACE content on. And this is September 10th, 9 to 10 a.m. Eastern by Teams. It's held by the GeoHealth air quality group. There's a link at the bottom if you want to learn more about their group or join this community of practice if you're interested in staying up to date with what they're doing. During the meeting, I'll give an overview of PACE atmospheric products and applications, and then we're going to have a great talk from Zach Fashnot, who will be talking about air quality applications from PACE OCI, notably the nitrogen dioxide and probably the ozone products that he is the PI of the algorithm for. We'll also have a talk from Omar Torres on the PACE UAA aerosol products and potential air quality applications. I don't have a direct meeting link for this one to share on the screen here, but if you would like to go to this meeting, you can join the group and they'll send it out, and you can also email me and I can send you the Teams join information. Other than that, we have one other big update that we're pretty excited about coming soon to your inbox. We're going to have a PACE community newsletter. Of course, you have to be subscribed to the PACE community email list to be on this. I'm assuming all of you are, since you're here and know about this meeting. And I put the wrong link there. That's the link to our events page. We have a different link that I'll put in the chat once I'm done with our join link to make sure that you are joined with the community of practice to get these newsletters. We're pretty excited about the newsletter. It's going to be quarterly and it'll update you on all things PACE. Our September issue is going to be, it's actually going to be our summer issue. So it's going to cover June, July, August, and it'll be released in the first part of this month. It's looking great. And that's all that I have. So from here, I want to turn the talk over to Kirk. One second while I transition my my own screen. So next up, we have Dr. Kirk Knobelspiesse. He is a remote sensing specialist working to improve our ability to monitor the Earth. He has expertise in radiative transfer calculations, information content, assessment, algorithm development, and validation with ground and airborne observations. Specific interests of Kirk's include polarimetric remote sensing of aerosols and clouds, atmospheric correction required for ocean color observations, and the statistical and AI tools useful for both. He's currently the PACE Project Science Team Polarimeter Lead and PACE Post-Launch Experiment Mission Scientist. From there, take it away, Kirk.
Okay. Well, thank you. And can you all hear me okay?
Yes.
Okay, I will go into full presentation mode. And okay, so I'm Kirk Knobelspiesse. My original plan today was to talk both about PACE polarimetry and the PACE PAX field campaign. And as I was putting the slides together, I just couldn't do it. So this is what we're really going to do. We're just going to talk about polarimetry today from my perspective. I'll give kind of a high-level overview, and then Meng will talk in a lot more detail about specific algorithms that are used for aerosol retrievals. I believe I'll talk about PACE PAX, the field campaign, in the next community of practice meeting. So just a little bit of background about myself. I've kind of bounced around in a number of different fields. I've worked in everything. I've worked on more theoretical things, and I've also worked on a lot of field work. So here's just some photos of me doing field work at both land, sea, and in the air. And so I'm going to talk about why we have polarimeters on PACE. And I'm sure you've seen this slide before. If you've gone to any PACE presentation, this almost seems like a requirement that we show this. And what we're going to focus on today is measurements from these two small instruments that were attached to the side of the PACE spacecraft, HARP2 and SPEXone. HARP2 is a contribution from the University of Maryland, Baltimore County, and SPEXone is from a consortium in the Netherlands, Esron and Airbus. Both of those instruments are what we call multi-angle polarimeters, and they're very different kinds of multi-angle polarimeters. So I'll talk a little bit about that in a moment. But generally speaking, what I would like you to come away with today is an understanding of what is polarization and why do we measure it, the products that we make from polarization, the level 2 geophysical products, And this will be for the next time around, but how do we validate those products? So if we step back a moment and think about the thoughts that went into the design of OCI on PACE. OCI has many capabilities. It's useful for many different disciplines, but one important aspect of this was the ability to observe ocean biology. And to do that, one needs to have a very subtle understanding of the color of the ocean. This is the picture that I took on the municipal wharf in Santa Cruz, California. I believe this was set up by Rafe Cadella's group at UC Santa Cruz. And this is just sort of indicating how the color is variable in the ocean, and that tells us something about what's there. So if you're designing a spacecraft instrument to observe ocean color, one of your best tools is to make very detailed spectral information. And so that's what OCI does. It measures a wide spectral range, and it has very narrow sensitivity, narrow spectral sensitivities within that range, so it can tease out all of the spectral nature. Essentially, what we're doing is we are maximizing spectral information content. And information content is sort of a theoretical term of how much information is available in a measurement for us to extract and turn into some sort of geophysical parameter we're interested in. So OCI's approach was to maximize spectral information content, but that's not the only sort of dimension of information that we have to work with. And some of the other dimensions are what the multi-angle polarimeters are making use of. So I want to emphasize that the instruments that we have on PACE, HARP2 and SPEXone are multi-angle polarimeters. So it's not just that they're sensitive to light polarization, which I'll talk about in a moment, but they are sensitive to multiple angle measurements of a scene. And so this little animation, which is from a nice video about the multi-angle polarimeters created by the Science Visualization Studio at Goddard, shows how we observe multiple scattering events off a particle as a spacecraft passes over, and that multiple pieces of information tell us about what's happening in the scene. So this is what it looks like, in a cartoon sense. Actual imagery might look something like this. Now, the GIF image I'm showing at the right here is from the early stages of the mission. So it's if you were to pull this data set now, it would look a little bit better. This is before some of the geolocation and calibration changes have been made. But what it's animating through is not time, but different viewing angles. And the important message here is that as you look at different angles, things change in the scene. And those changes tell us something more about what's present there. So you can see that flash that's sort of at the bottom left there over the ocean. Oh, that's sun glint, and sun glint only appears at specific geometries. You can see actually a little bit to the right of that, and up if you stare hard enough, another kind of feature that happens over land. That's land surface BRDF. I believe it's the backscattering direction. And if you look at the clouds, you can see how there's some parallax impact on the position of the clouds. These are all pieces of information we can use to understand what's in the scene. Now, a little bit harder to visualize is the impact of scattering from aerosols in the scene, but this is also equally important. And really, it comes down to something like this. When we're making a measurement, what we're looking at is how, in a bulk sense, light scatters off particles that are present in the scene, aerosols. This also applies to cloud droplets. And so what's being shown at the left here is something called a scattering phase function. And really, that's sort of the probability that light, when it interacts with a particle, of which direction it will go. So the way this is drawn here, light will tend to scatter more in the forward. It's more likely to scatter in the forward direction than the backscattered direction. But different types of particles, different sizes, different chemical compositions, have different scattering phase functions. So they scatter light differently in a directional sense. So if we measure the light scattering off these particles at different directions, we can get a better understanding of the particles themselves. And this provides us with more information and a greater ability to determine the inherent optical properties of aerosols and cloud droplets. Now, what an actual measurement might look like could be something like this at the right here. This is pulled from a HARP2 scene. So the x-axis is a sensor view angle. The y-axis is a reflectance, and we have for HARP 4 different wavelengths of light, or spectral channels rather. And you can see that generally speaking, there's the angular change in reflectance is a smooth change. It's generally a subtle change, but there is information there that we're working with. So that's one aspect of multi-angle polarimeters. And the other aspect, of course, is polarization itself. And so what is polarization? Well, if we think of electromagnetic radiation as waves, those waves are oscillating in a particular direction. Sunlight, as we're aware of it, is unpolarized. That means the assemblage of light, the group of all the light that's arriving at the Earth from the sun, has no preferential direction. It's a mix of all sorts of different directions. However, when that electromagnetic radiation interacts with something in the atmosphere or on the surface of the Earth, the scattered radiation can have a preferential oscillation direction. In this case, that light is considered polarized or partially polarized. So this is an example that might be something like, say, a smooth surface of the water. And so the light that's reflected from this water would be polarized. This is, for example, why we have polarized sunglasses, that those polarized sunglasses are blocking light that's polarized in a specific direction that's usually associated with reflection off of surfaces sort of parallel to us, or I'm sorry, parallel to the surface in front of us. So how do we use this information? Well, I just wanted to demonstrate a little bit about what this looks like in nature. I took this sort of uninteresting photo a couple of years ago outside of an office building. And this is the total or sort of unpolarized expression of this scene. And you can see that, you know, the sky is a blue, the grass is green, you know, the shadows underneath the trees are dark. And we have sort of an intuitive understanding of how it should be looking. If we were to look at it in another unit, this is the degree of linear polarization. So the brighter it is here, the more polarized as a fraction of the total amount of light that portion of the scene is. You can see that this doesn't look like anything that we have an intuitive understanding of. Things like there's not a lot of color of land surfaces except for these weird bushes here that are kind of blue. The sky has sort of a gradient to it that's kind of strange. All this is other information. All this tells us something about what the light has interacted with. And this is what the polarimeters are trying to make use of. To show you what this looks like with actual imagery, before I showed an animation that stepped through the different angles of HARP data. This animation is sort of a true color, so it shows us the true color image at different angles, and we're iterating through, or we're stepping through both intensity and polarization. So you can see that when we flip to the polarization, the label's at the top here, it looks quite different than the intensity itself. So again, this is all information that's particularly useful for us. Excuse me. If you look at the acronym for HARP in particular, it's a hyperangle rainbow polarimeter. So there is a particular feature of cloud droplets that we're making use of as well. So if one were to look at the Earth from space with polarization sensitive eyes, you would see rainbows everywhere. And that's because liquid cloud droplets highly or create a cloud bow, not a rainbow. Rainbow would be off rain droplet sized particles, but off of smaller cloud droplet sized particles, you create a similar phenomena that looks like what's shown in this image at the right here. This is a useful piece of information because it tells us very precisely the size distribution of the cloud droplet particle or cloud droplets. And so this is something that we're making use of with the HARP2 instrument. So just a quick note about the two instruments themselves. HARP2, which I've mentioned and I've shown some animations from, has 4 spectral channels. but it has lots of viewing angles. In fact, one of the channels has 60 viewing angles. And this is a wide swath instrument. And that's why I've been showing imagery from this, because it has a bit more context. SPEXone kind of takes a different approach. It just has 5 angles, and it's a much narrower swath. But like OCI, it is a spectrometer. So it has lots of information in another dimension. So these two instruments are a very nice complement to each other. And we have a number of different algorithms that are creating both cloud and aerosol products, but not exclusively cloud and aerosol products from these instruments. So for example, we have some very interesting algorithm, or a very interesting, I guess, package of algorithms called the GIS polarimetric cloud algorithm suite. And this is retrieving cloud droplet size distribution and other information from the cloud bow on HARP. That's available now. Everything on this page here in green is available now. For aerosols over land, RemoTap, which is one of the retrieval algorithms for SPEXone aerosols. So this is a simultaneous retrieval of both aerosol and land surface properties from RemoTap. RemoTap has been out for a couple of months now. GRASP is another algorithm we're in the works of putting into production. Over the ocean, we have a couple more algorithms to work with. Meng is going to talk about FastMAPOL in a moment. FastMAPOL has been implemented for both HARP2 and SPEXone. RemoTap, of course, is also working for aerosols over land and over the ocean. And finally, MAP, which is in development, is available for aerosols over the ocean. MAP, when it's fully implemented, will actually combine data from all 3 sensors on PACE. So that's sort of where we are right now. If you want to learn more, you can go to the PACE data product table. We do our best to keep this up to date as to where things are, what stage of data release they are, and more documentation about them. So before I hand it over to Meng, I just wanted to give or show some sort of quick results. We've been making these things we call science nuggets. So, sort of 1 or 2 slide encapsulations of some interesting things from PACE. So this is a couple months old. This is sort of a first year of observations from SPEXone with the RemoTap algorithm. And you can see the rich information content that the SPEXone instrument has for the purposes of aerosol retrievals. So we're able to retrieve not just aerosol optical depth, which is shown in the top center here, it's sort of a mount of aerosols, but descriptive properties of those aerosols themselves, such as single scattering albedo. This is how absorbing the aerosols are. And you can see, for example, these blue areas, which are highly absorbing and are associated with biomass burning smoke. There's a fraction for dust, and obviously you can see the Sahara Desert right here, and some other properties as well. So this is a very useful data set if you want to, for example, improve models of the atmosphere. Moving over to clouds and to the HARP instrument, this is a product that's out now, the GIS polarimetric cloud, a GPC cloud. And this is a measure of both cloud droplet effective radius, but also the effective variance of the cloud droplet sizes. So effective radius is more or less telling us the mean, or the sort of centroid of the size distribution. There's a couple of different size distributions plotted at the left here, whereas the effective variance shows us how it's spread out. And that's related more towards cloud lifetime, or where the cloud is in its life stage. And this second piece of information, effective variance, it's something that we didn't have at this spatial resolution before PACE. The only equivalent was on the order of 250 kilometer spatial resolution. Now we're down to about 5. So this is a first ever, and we're really excited about exploring this data set and seeing what we can learn from it. And finally, this is the last one I'll show. I do want to point out that PACE being a multidisciplinary mission, there's a lot of opportunity for measurements from multiple domains and relating them together. So this is a nice slide that shows how we can relate both aerosol atmospheric aerosol retrievals to land surface changes after fires. And so these are the unfortunate fires in Southern California in January of this year. We see that smoke plume from the fire in terms of optical depth, and the other properties retrieved from, this is from FastMAPOL and HARP, by the way, help us identify conclusively that this is smoke and differentiate it from a dust plume farther south coming off of Baja California. But we can relate this then to changes in land surface. So this is a product we're creating that monitors burn severity. This comes from OCI, so can relate both the land surface and the atmospheric effect of these fires simultaneously. That's all I really had for now, and I'll talk, like I said again, next week about PACE PAX. Are there any questions that people have or discussion that you'd like to have?
Any questions for the chat? You can type them in the chat and we'll get them answered.
We can also move on to Meng's talk, which goes into more detail about FastMAPOL, and I can take questions at the very end as well, or both of us together, as you wish.
All right, excellent. Thank you very much, Kirk. That was fantastic.
Thank you.
Yeah, appreciate that presentation. And we will turn it over now to Dr. Meng Gao. He's a research scientist, also with us in the Ocean Ecology Lab at NASA Goddard. His research interests and expertise include light scattering theory, radiative transfer simulation, optimization algorithms, and deep learning. His projects focus on the remote sensing of the atmosphere and ocean color. He currently supports the PACE mission in developing aerosol and ocean color remote sensing algorithms with the multi-angular polarimeters and is the lead developer of the MAPOL and FastMAPOL retrieval algorithm. Today he's going to be giving us a talk on the FastMAPOL Polarimetry Data Products, including some applications to ocean color, and he's also going to give a data access demonstration at the end. Take it away, Meng.
Thank you, Morgaine. So I will just follow what Kirk has been talking about. Take a really nice introduction. So here we will dive in more details on one of the particular algorithm, FastMAPOL, and we'll talk about the status of current data product, and also some of the gaps, challenges we have been facing. That is something we have been working really actively. So I think Kirk talked about he have work on really different product and background. So for me, I have a kind of similar story. So I work on in my PhD, I work on optical properties of the marine animals. Actually, we study a lot of different types of small particles, but in the skin of animals. And also, I spent a couple of years work on acoustic waves on the ocean bottom. But we use like polarization-related techniques, and all that lead me to work on PACE. So Kirk has been talking about what we have from PACE, and there's a lot of capabilities here. And the data product we try to produce that include a long list. And so I just want to highlight some of them here. So for aerosols, we will produce like aerosol optic properties, aerosol optic depth, absorption, and also aerosol microphysics properties. And that is thanks to the capability of polarimeters, we can get aerosol size, aerosol shape, and the reflect index. And we can also derive aerosol layer height and also surface properties depending on looking at land or ocean. And Kirk have been also give us a really nice overview of what we have in terms of the algorithms. So just want to say here for random type, you can get data from our data server and also from our data cloud. And for FastMAPOL, it's only on our data server, and it's all over ocean only. And the grasp and map, we have been testing them. The data will be ready soon. And for this page, I have I put some links how we can access the data. For FastMAPOL product, we have it in the forward stream since this July. So that means you can see this product every day since July 1st. And there are also some data we processed to support the validation. So that include during the PACE PAX months last year and also this January. And the data is we have 1 day latency. So actually, I look at the data just today, I can see the data from yesterday already produced. I don't know whether Sky, you can maybe copy the link there if you're not already did that. So you can click the link to see what data is there, and so basically this will be similar for other algorithms too, including Raman type data. And we also have some level 3 data available. That's with the global maps. So some example I'm showing on the right for aerosol object types and ocean remote ocean signals. So this we have 2 months data. So you can probably see level 3 data for only 1 month at July, and we have a 1 day and 8 days data there too for the whole month, for 2 months. And eventually, so at the end, I will show you some demonstration to how to access data, make some simple plot to some analysis. Okay, so let's dive in more details. So the first thing I want to emphasize is our retrieval algorithm, our analysis based on rigorous retransfer model, and this model is developed by Peng Wang, and he have worked on it for maybe 20 years. So this is vector retransfer model, and it's include many very useful features that include the atmosphere and the surface coupling, and also consider realistic atmosphere geometry, and with the polarization and gas absorption and many other very advanced features. And this will be the foundation for our discussion and for the retrieval algorithm development. And the drawbacks, the only drawbacks is the retransfer model is slow, although it have really high accuracy, a lot of great features, but it's not suitable for operational data processing. So we spent some effort to represent this physical-based retransfer model into a neural net, and this is like one of the early model we have been developed, showing here. And we also try to optimize the structure of the neural net to get maximum performance in terms of accuracy and speed. On the right plot, I'm just showing you the complexity of the neural net on the y-axis, from like 64 nodes with 2 layers to like 500 nodes, 3 layers. And the vertical, I'm showing you the accuracy compared to the measurement uncertainty. Basically, we can control the accuracy by using more complicated neural net, also adding more data. And in this way, we can using the base neural net with the base accuracy for the retrieval, and also we can use a smaller one with faster speed to get a good first guess. In this way, we can optimize both speed and accuracy. So build on that, so we have been working on this retrieval algorithm called FastMAPOL for 30 years. And what we want to do is we want to optimize 3 things. The first thing is the model itself, that includes the aerosol model and ocean model. We want it to have a flexible treatment, and what we want it to have a great efficiency, which we can use in production processing, and also we want to have a good understanding and uncertainty. Basically, this is a kind of work we have been working on following the years. I won't get into too much details, but basically for the model part, we have several aerosol and ocean model there, and we build for the efficiency, we rely on the neural net. Also, we can derive Jacobians, and we can also play with the neural net to get the first guess and other things. And for the uncertainty studies, we work on the error propagation. So you can using the measurement uncertainty to understand the target uncertainty from level to product, and we can also look at how the number of angles impact retrieval uncertainty, and also the geometry, orbit geometry, and other things. If you're interested, you can maybe take a look at our papers. I won't cover too much details here. So one thing I want to say is, so we do conduct like a realistic simulation before PACE launch. This is called so-called day in the life test. So have a realistic HARP2 simulation, and based on that, we do some uncertainty analysis. We can compare our retrieval and the truth, and then we can also look at the error propagation uncertainty. That is basically that's what the theoretical uncertainty we do expect. If these two match each other, that means our retrieval kind of achieve the maximum performance. And there is one highlights here for aerosol object types. You can see the retrieval uncertainty and kind of a gray reveal from a theoretical uncertainty. We have been also look at many other variables. And basically, that's true for most of the variables, but it's become challenging for coarse mode aerosols. We see our retrieval, the performance kind of larger than the theoretical uncertainty based on error propagation. And so that means we should be careful about coarse mode at least. Okay, just show you some animation. So this is what we have after 1 month of the PACE, 2 months PACE launch. So this in the 2024 April. So we process whole month. You can see how the aerosol propagates globally. So because HARP2 have really nice coverage, so you can see really nice global maps to see aerosol transport. And we also look at more details, and Kirk have showing this example. So we look at aerosol absorption, aerosol size, and other properties. And so the demonstrator I'm being showing actually is based on this case. I won't talk too much about this. So hopefully we can use the notebooks to showcase this example. And another thing we have been focusing on is how we can improve, while we improve aerosol property, we also want to have some understanding or improvement on the water leaving signals from ocean. Because HARP2, SPEXone, they all have a multiple angle capability. So we're very interested to develop multi-angle water leaving signals. So what we can do is we can, based on the aerosol retrievals, we can derive the path reading in atmosphere and ocean surface, and then we can do the so-called atmospheric correction for all the angles from HARP2 and SPEXone. In this way, we can get the water leaving reflectance as 90 angles from HARP2 and 5 angles from SPEXone. And this result I'm showing you here is the water leaving reflectance, which we call the representative reflectance. So that's the we do the average of all the angles after we apply the BRDF correction. So you can see really nice pattern from both instruments. And in the data product file, we also include this product before and after BRDF correction, if you are interested in that. And for more applications for this angular RS, you can also refer to one of Xiaodong's work published this year. They have been using the angular reflectance we derived based on the daily life test from HARP2 simulation. So it's very interesting. So I will show you really quickly about our validation effort, because many products are really new, and so it's not easy to validate them together. So we have been looking at the 3 data levels. For level 1 data, we can look at whether, from the reflect and the polarization, whether they agree to each other. And we can also look at whether they can agree with our return model. We actually include one of the quality masks in the level 2 product, which indicate like how well we can fit the measurement using for a model at each angle. And for level 2 part, so we've been using PACE PAX data, and we also use the RNAV data. I will show you some results in the next couple of slides. And we have been also spend a lot of effort trying to compare the product from different instruments, HARP2, SPEXone, OCI, and also from different algorithms, as Kirk have been mentioned before. For level 3 data, basically we can look at the global pattern, right? So very easy to identify major events and patterns. So, and there's also would be very interesting. We can also compare with other satellites. There's some ongoing work with that, also with models. So the first thing I want to mention is, as I mentioned, so we try to have some understanding whether the form model can fit measurement, right? That's the basic thing we try to confirm, and also like which angle or which measurement cannot be fitted. That will indicate some of the either calibration or the form model assumptions. And I'm showing you some example here. On the left, that's the RGB plot from HARP2. On the right, it actually is the number of total measurement or time from HARP2, which can be fitted within a certain criteria in the level 2 retrieval per size. And the red color basically means we can fit most of the data. Here we can, total we have 90 angles from HARP2, we can fit most of them. In the center part, we have some difficulties. There's some strange behavior from Sanglint. We're still trying to understand. And also near the cloud edge, you can see there's there is not that any angle can be faded. That's mostly because the 3D effect of the cloud. So I'll show you some validations. There is one example from the PACE PAX. We compare with the LiDAR, the HSRL, as this at one of the day. And on the right side, actually, I have the flat tracks overlaid with HARP2 AOD retrievals. You can see the flat tracks with the LiDAR AOD kind of being invisible there. That's because they kind of match each other very well. Here is just the land cloud. You can see they kind of match each other very well, except on the cloud edge. And there's another one. So I've been showing you the number of value angles on this thing. So we have some challenge our Sangolin area. Also, they have a lot of a really strong wind speed. We do see there's a nice trend there, but we are still working on with the LiDAR team and all the other algorithm team to understand this. But the good news is we have data. We can investigate further. Let's show you very quickly on the validation with AeroNet. So for HARP2, we still have some challenges. Although we get a good correlation, but we still see like a bias there in order 0.07, 0.06 for most of the land. And so we can also validate the ocean color product at the same time. So here we are using the AeroNet ocean color set. We have aerosol properties. We also have the water limit reflectance. So we can validate them together. So with the positive bias from AOD, we also see negative bias from the remote sensing reflectance. So that means our retrieved aerosol, our retrieved water signal is kind of smaller. That's kind of compensated by the AOD. So we are doing active research to understand this. This can be related to the calibration or our model assumptions. And in order to really pin down what really happens, so we also process the SPEXone data using the same algorithm. So here is a validation you can see here. And this because on SPEXone we don't really have that many matchups. But basically we can see that the bias is much reduced. And also this is also true for the remote sensing reflectance. So this can be there could be several reasons. So we actually trying to compare all the other variables, including aerosol size, effect index, and try to understand like where so why it works for this for the specs data, and where the cause for the bias from the HARP2 data. And so this one of the challenges is also related to the number of the valid angles, so the information in the data. So we have included all the quality flags, including chi-square, the fitting cost function, and also the number of valid angles, those information in the product file. And you're welcome to take a look if you have some ideas. Anyway, so here just come back to this slide, and I don't know what Morgaine, you want we have some question here, or I can just go straight to the demonstration.
I'm not seeing questions just yet, so how about you go on to the demonstration and we can see what there is afterwards.
Okay, sounds good.
Thank you.
Right, so if you have any other question, you have difficulty to access data, we can also discuss. If you click this link, I believe you is can you confirm, Morgaine or Sky?
Yep.
Have you have the link there? Okay.
Yes, we have it in the chat.
Okay, great. So you can click the link, and or you can just watch me going through this. So this is a notebook we created for the PACE Hack Week, and this is based on a Jupyter Notebook. So you can download the notebook here, and run it under Python environment if you have, and if you do not have it handy, so I can just go through this quickly. Basically, we demonstrate how we can access HARP2 data and understand basic data structure. And this will be also true for almost all the current HARP2 SPEXone level 2 aerosol products. So we have the same file structure. So you should be able to work on the same all of the products using the same notebook. Basically, so we rely on the Earth access module, and so we can use this module to download data. directly from our data server. And for remote type products, the data is also on our data cloud, and this tool can also help you to play with that. So here is also a tutorial page. This will link to our PACE HARP2, and there are a lot of useful information. And if you want to learn more about the cloud access, other things. So basically, when you open this file, and you see there are several data groups, and here we can use an X-ray. So if you look at data groups, I have a geolocation data group that include all the geolocation information, and we have geophysics data that include all the variables, the retrieval variables. We have error to layer height, if you see here, and wind speed, and many other things. And one thing I want to mention is we also have the representing reflectance. And in this case, we have the mean value and the standard deviation because they have angular variability. In the newest data product since July, we actually include the full RS, full angular distribution RS. So you will see them there. And then you can look at there's the so-called diagnostic data that include the fitting chi-squares and the number of valid angles, and also we have angular data mask. And this variable really, those are really important for us because many of the products still under investigation. So those are the variables we can look at all the time to understand data quality. Okay, so as I mentioned, there's many variables here, and I don't have to repeat this. So we can look at the few variables here, and we can pull out the AOD or AOT, or single signal albedo and the thermal volume fraction, and also the light long, to have a little function here to make plots. And here we can see this is exactly the same plot Kirk has been shown. We have the smoke here due to the wildfire, and we have a dust event. And here is the single signal albedo, and this includes everything, the whole thing here. And you can see this part we don't have much absorption. This part we have more absorption. And here is the thermal fraction, basically more thermal in this area, less thermal in this area. And you can do many ways. You can have many ways to screen data or play with data. So one thing is because for the case with low AOD, the microphysics retrieval will have large uncertainty. So one good way to look at this thing is that you can screen out the low AOD pixels, and you can highlight these two events for the absorption and thermal volume fraction. So eventually, so this is for quality assessment. I've been mentioned about this. So we look at the fitting cost function. That will be the chi-square, also the number of valid angles, because in our retrieval algorithm, we screen out the angles which we have large fitting residual. So that means if we cannot fit that angle, we remove it. And in this way, we can kind of control the chi-squares, but we also should be very careful because the number of valid angles kind of direct indicator how well we can fit that the pixel. And if the number of valid angles is small, that means that pixel will have a large uncertainty because we don't really have much information. And we also put them together to have some kind of quality flag there. And you can make a plot for the chi-square, and basically they kind of center around the 1.5. It still have a little bit of overestimation or overfitting. And also the valid angles. And in this case, it's for reflectance. You can see we can fit the reflectance on most of the region, but near the edge, and also there's some region there that happen. We need to take a further look. This is a direct indicator, like the performance or the quality of the level 2 product. And for the polarization part, this you can see we also have some spatial dependency. Also, we have more challenge to fit polarization. And currently, we feel maybe this will explain why we see some bias in the level 2 product, and because of this kind of challenge to fit polarization measurement, but it is still under investigation. And also the quality flags here. And the quality flag is most important for the level 3 data. In the level 3 data, you will see there's a variable called quality flag, which indicate like whether the quality of the pixel which is used to to create that level 3 product, and that will be very useful if you want to understand which region have a better quality than the other regions. And eventually, so we can also look at the multi-angle data mask. And if you're interested in the level 1 data itself, you can use this data mask to have some understanding like how the form model can be used to fit measurement, which may relate to the calibration of the measurement itself or other artifacts. And so we have that for reflection and polarization part. So you can play it with different angle here. Okay, so I think that's pretty much all I have. And we don't have include the pixel level uncertainty in the products, but we have a few papers. We kind of have some analysis on that. So I will stop here and come to questions if you have anything for me or Kirk.
We did have one question that I'll just go ahead and read out loud. It was answered, both Kirk and Andy answered, and of course, Meng, if you'd like to add on, feel free. The question was, I know the aerosol index is being produced at native OCI pixel resolution. Is there any other parameter available at similar spatial resolution? Kirk said, we're getting there. It's easy to compare RemoTap and FastMAPOL products since they are on the grid. They inherit from the L1C files. UAA from OCI has a different resolution grid, so that is a bit more involved. And then Andy said the only aerosol property written out at full resolution from UAA is the UV aerosol index. The file also has the aerosol residue used to compute the index and LER though. Is there anything you'd like to add to that, Meng? Do you want the original question?
Yeah, I think Kirk and the answer as well. And yeah, so for the polarimeter product, basically it's on the level 1C grids. So the grid size is 5.2 kilometers. That will be different with OCI. So yeah.
Yeah, and there's a few more coming in. Is there some validation documentation for the HARP2 aerosol products?
Yeah, we have a few papers based on the simulated data and also airborne data for the PACE HARP2 data itself. We are still working on the paper, and we have many slides I would like to share with you. And if you you have interest, and we don't have a fully written documentation yet, but we do write down some known issues in the data release note. I think it's either Sky or Morgaine shared that in the beginning. You can see we have some like document or simple highlights was known issue as I mentioned in this talk there for both the HARP2 and SPEXone and level 2 data.
And if I could add to that, this sort of information goes into a ATBD, an algorithm theoretical basis document. And we are still in the progress of making complete ATBDs for all of the products. But when those become available, they're listed in the data product table, which I think we've linked and I can put in the chat. So for example, the RemoTap algorithm from SPEXone has an ATBD, and I believe it has some validation information in it as well. So that's where it will go as we fill it out. Just to read through, if you run into problems working through the tutorials, who should we reach out to? What do you think? Is the Help Hub the best place?
Yeah, I think eventually the notebook will be in Help Hub, right, Karina? So if you are talking about HARP2 notebook, you can reach out to me, and we can figure out what happened. And if you have questions on the other notebooks, we have a team people here who can help you too.
All right, great. Also, I incorrectly read the answers to the questions earlier. I didn't realize there was 2 questions. I'll paste the correct question and answer in the chat, FYI, for anybody that was caught the answer that was for a different question. So there's a couple more questions. Is it possible for me to learn about the GPC algorithm?
I'm writing a response, and I'll put some links in the chat. All the algorithms, if they don't have an ATPD in the data product table, we have papers that they're based on. You can also write to Meng or myself if you have more questions, and we can put you in touch with the lead for those algorithms. I don't know if he's on the call now, Shamaraj Bakshi. But I'd start with the data product table, and I'll put some of the links in the chat right now.
All right, excellent. We have another one from FastMAPOL. What is the maximum AOD level permissible for retrieving water-leaving radiance simultaneously?
Yeah, that's a good question. So we don't really limit the AOD level, but you will see probably higher uncertainties when there more AOD with more aerosols. So that will be part of the uncertainty analysis. Basically, you will see water-leaving reflection there for all the AOD scenario, but you probably will see large uncertainties when there's high AOD. Currently, for the AOD, we use mostly it's within 0.5, but there are also high AOD case there.
All right, excellent. Looks like we have one more. Oh, they said thank you for that answer. When averaging multi-angle remote sensing reflectance, do you account for solid angle variation for different viewing angles?
Yeah, that's really good question. I haven't really think about that. You talk about a different view, maybe the solid angle are different, right? So, yeah, I don't really have good idea how much that will contribute to the RS. My guess is maybe not that much. So one thing we want to make sure is we are on the same page is for the RS when we do the average, so only the one after we do the BRDF correction have the real physical meaning, because they are kind of corrected to the same wavelength geometry, basically as nadir. So I'm not sure like how much do we account solid angle in the BRDF correction. That's something I haven't really think about before.
All right, excellent. Does anybody else have any other questions? Okay, well, this was fantastic. Thank you, Meng, for that excellent presentation, and also including that demonstration there at the end. We want to also thank Sky and Karina for helping with pulling off today's telecon there in the background. And I also want to remind everybody that our next telecon is actually going to be pretty soon. It's going to be in a month, and it's going to be Polarimetry Part 2. I put a link in the chat to the agenda, and we're going to get to hear about some more of these great polarimetry products. We'll hear from Chamara on the polarimetric cloud products that are coming out from PACE, as well as we're going to hear about remote tap polarimetric products. So please, watch your email for that team link, the Teams link that you'll get for that telecon. And again, I want to thank everybody. Thank you to the presenters. Thank you, Kirk and Meng, and everybody that helped out with this telecon. That's it, and we will see you in a month. Thank you.
Thank you.